So I'm taking that as a positive. That's the only way I can think to look at things is, hey, all right, what's done is done. Let's try and be better because of it.
Now, to be a little wild, could I ask about a physics question? Because I'm looking on the online right now, and you think you could do number 15?
15?
Yeah.
Number 15. So let's try something here. Let's do this. And let's do this. And let's do this. All right, so you should see my screen. And if I remember, is 15 the one that has two capacitors being combined together?
Yes, it does.
Okay. So this right here, let's see what slide this is. This is slide number 32, as you can see right there. So slide 32 is the best way to go about doing this one. So what I see here is you've got your two plates in my picture. This is not number 15, but just this is a way to explain it. Here's my picture. I've got two charged capacitors. When they come in contact, I see that I have plate, metal, and plate all there. So this whole top half is all connected. So they're going to share the same potential as down low. So if I look over here in blue, two capacitors, they act in parallel, and they will share their charge until, right here, until their charge distribution is equal. That way I have the same field for each. Otherwise, if I had a stronger, more dense charge distribution, I'm going to have a stronger field there pushing charges off of it. So having said all that, I'm going to scroll down now. And I know that when you see my screen, I don't think it is as smooth as when I'm actually doing the keystrokes here. So I'll try and keep that in mind. But what I have here is an example. I've got a potential and a capacitance, so I can figure out the amount of charge Q1, I'll call it, here. I can also figure out the charge over here, call it Q2. And that's before they were connected. Once they're connected, they're going to share. What makes number 15 a little bit more challenging, and what makes this concept more challenging, is if I scroll down, there are two ways to share charge. So step one, find Q of each before. Done. We've done that right there. QVC, I can figure that out. Number two, when they are closed, they will share their charge. So you have to show the share. This is what's important in blue. The share can be done one of two ways. The picture I have shown you here shows you two positive plates coming in contact with each other. So all the positives are going to be shared. If I have, and I believe number 15 says, what happens if you have a positive end coming in contact with the negative end? Well, what's going to happen is I'm going to have positives leave the positive plate, go onto the negative plate, neutralize it, and then I'll have a few more positives go over there, and I'm going to end up with a lot less charge stored up than if I had positives in contact with positives. So when you're doing a question like this, scroll back up. Step one, find the charge of each plate prior. Step two, show the combined total, and that's where you have to think about it. Okay, do I have positives touching positives and negative touching negatives? If so, you add them up. If I have them reverse polarized, if I have a positive and negative touching and a negative positive on the other side touching, I'm going to have some cancellation. So it's quite simply a subtraction instead of an addition. Once I have my total charge, so QT, my total here in my example would be the 1200 I calculated minus the 250 I calculated, gives me a total of 950. Had I connected them positive to positive in my question, I would end up with 1450 stored up, not 950. Regardless.
So the 1200.
Say that again?
The Qs on each capacitor.
Say that again.
Sorry, the Qs, or sorry, the 1200 and the 250 are the Qs on each capacitor?
Yes, those are the Qs on each capacitor that I calculated right here in blue. So I've got,
okay, gotcha.
I've got 120 on a 10, which gives me 1200. And then I had what do I have there? I've got 50 volts across a 5, which gives me the 250. So those were calculated. They could be given, I suppose, but those would be most likely something you would calculate. So I've got those two charges. That's where the 1200 and the 250 came from. Now that I have my total charge, now I continue on down here in step 3. oops, I'm drawing instead of moving. Come down here, step 3 is what's your total voltage and your total charge? Well, the voltage is going to be the same for both of them. So I take my total charge, I take my total capacitance, which they act as if they are in parallel. So I've got a 10 and a 5, and in parallel, I just add them up, so I get 15. So I come down here, and I take my 950 for Q. I've got my 15 for my CEQ, and I use my QVC equation. I figure out what V is. The V of the whole thing is the V for 1, it's the V for 2. Once I know what V is, I can do QVC to find the new Q1 and the new Q2. It was 1200 and 250, now I'm gonna end up with 2 new values. Each capacitor, since it has the same voltage, each capacitor is going to hold a different amount of charge because they're different sizes. To me, it looks like this one is twice the size. With the same voltage, this thing should be, or should hold twice as much. So that's conveniently, that's what my example shows here. Question 15 might not be nearly as convenient. So find charge of each, QVC. Add or subtract your charges together to get the total based on how they're connected. They have to tell you how they're connected. And then once you've done that, once you do that, you use QVC, but use total. So Q total equals V total times CEQ, which was the sum total of our parallel system. And V is the same for the total, it's the same for V1, and it's the same for V2.
Could you zoom out a little so we can see all the steps together?
Yeah, let's see if I can do that here. Whoops, okay, let's try, that didn't work. Let's try this, no. Nope, okay, let's try that, touch. There we go. And obviously if you have it open and convenient, you can use your, I have this posted on Edmodo. Actually, I kind of have switched over to using Google Classroom just to keep everything in one spot. But yeah, so that should be everything right there.
That makes a lot of sense. Thank you very much.
Yeah, and I don't know why. I don't know why I didn't finish the answer, finish the problem. So I will finish this question on slide 32 right now so you can make sure you're getting the same thing. So I've got 950 and I've got a total capacitance of 15. So my new voltage is going to be 63 1/3. So call it 63, which means that both plates, both capacitors, I should say, get 63. So using my cursor here, so this one has 63 volts now, and this one has 63 volts now. Now that they both have 63 volts, I can figure out what my total, I'm sorry, I used my total Q, 950. I used my capacitance total of 10 plus 5, 15, and I got VT of 63 1/3. So I'm going to take my calculator, I'm going to take 63 1/3, and I am going to do QVC for the first one. So that's going to be times 10. So 63 1/3 volts times 10 microfarads gives me 633 coulombs, microcoulombs for Q1, I'll call it. If I do 63 1/3 and I multiply it by 5, I get 316 2/3, call it 317. And to double check my work, 317 plus 633 equals 950, 950. So looking at my screen right there, that total 950 stays the same. It's just been redistributed. So instead of 1200 and 250, now I've got 633 and 317. So it's been redistributed a little bit, and it's caused a drop in potential on this plate and an increase on this plate. So again, that slide number 32 right there, slide number 32 is the best way to go about solving question number 15. Any other questions?
Yeah, I also had a question about dielectrics.
Yeah.
So when you have a dielectric, the equation was like your dielectric constant multiplied by, what was it, the shoot, dielectric constant multiplied by
Epsilon naught.
vacuum permittivity, something like that,
Mhm.
and some other constants.
Yep.
So would that be the equivalent of having your dielectric constant multiplied by the capacitance?
Yeah. So can you see my screen right here?
Yeah.
Look at your screen. So you've got this right here is my dielectric constant, which is actually calculated by doing the new capacitance I have with the dielectric divided by a capacitor with no dielectric. So that's how we find K, and then I can bring that down here, and I can plug that into I can multiply that by epsilon naught to get the permittivity of this new dielectric. I can look it over here as well. This right here, epsilon naught A over D, this is CO. CO times our kappa equals C. CO times kappa equals C. So I can see it a couple different places there. About question number 21. Let me look at, let's see, I've got it somewhere here. So I know you can't see my screen. I'm pretty sure you're looking at me right now, but I'm looking at my screen here. Question number 21, a capacitor network with air-filled capacitor is shown. And then what we're going to do is it says when the top right-hand capacitor is filled with a material of a dielectric constant, the charge of this capacitor increases by a factor of. So we have a system that is still connected to the battery. So since we still have the battery, so let's do this here. So let's try something new. Let's try this here. So you've got a battery, and then you've got up here a capacitor, down here a capacitor. Sorry about my finger not being as. So there you go. So you've got your 4 capacitors there. And so, can you see my drawing tool? I think you can probably see that.
Yeah.
Okay, so this will be my pointer. So you've got your 4 capacitors. So what you can do ahead of time is you can go through and you can figure out, okay, combine these 2 in series, add the reciprocals. Put these 2 in series, add the reciprocals. This branch and this branch, they are in parallel. So once I figure out each branch, just add the branches up. So what you can do is you can go through and you can find all of your charges and all of your voltages everywhere. And once you have that, you'll know how much charge and voltage you have on this one right here. And once you know what that value is, it looks like they gave us, can you guys see the UT assignment now? Or just the whiteboard still?
Just a whiteboard. for
Okay,
me.
so I'm looking at the online again. And so it says, let's see here. So increases by a factor of, yeah, so what you can do is we know that our dielectric constant is going to be a ratio. So if the charge on the capacitor increases by a factor of this, so, okay, so you'll have Q and V change a little bit. So what I see, let's see where we at here. Get back to my board. There we go. Pardon me. So what I saw is that every single capacitor was the same size, which means that these 2 branches here are each going to have the same potential. So whatever your voltage is, this branch has that voltage V, this branch has that same voltage V, and if I have 2 capacitors on one path that are identical, they're going to share that voltage and they're going to share it identical. So what I quickly find is that this right here is V, whatever's given. So just like that, I got V, I got Q, and I've got V and I've got C. So with V and C, I can very quickly find out what Q is going to be for this capacitor right here. And now they say that by sliding in a dielectric, I end up with this new amount of charge. Okay, so I got to figure out my new amount of charge, and I can figure out what from my voltage will be then, because I know this capacitor here, this capacitor here, I can express as, no, let's not do that. I can express that as K, which is what I'm trying to find, times my original capacitance, which is given to me. So I can do, that branch is going to be 1 over CO plus 1 over K CO. So it gives me, in series, so that gives me a way to kind of work my way through finding it piece by piece. So I can kind of leave that up there. So let's see here. Yeah, so they're telling us how Q will change. So they find Q and then put in that factor, get a new Q. Your voltage is going to be different. This capacitance is going to get bigger, which means that it's going to require less voltage. So V is going to get a little smaller. So don't just use the V you used at the first part to the second part. Find Q, multiply by the new factor, and then, like I said, you got voltage being shared across the two. And you can take it from there. Does that get you a start? Bye, everybody.